You've been hacked. Those three words can be the ultimate gut punch. When you read them, any feelings of safety and security get ripped away. Whether it's your personal messages, your social media passwords, your bank details, your company files, or anything. The consequences of having messages that were once private become public is an awful feeling with potentially dire consequences. So it's no wonder that truly unhackable encryption is such a sought after technology. And China may be leading the way to just that. How? It's all thanks to a tiny Chinese satellite, a record-setting experiment, and a tantalizing new technology, one relying on that magic word, quantum. And according to scientists, the method China used, quantum key distribution, promises to be unhackable due to fundamental principles of quantum physics itself. But what is actually going on beneath all the hype? Are we really at the dawn of an impenetrable secrecy forever? Or will that enigmatic word, quantum, be the death of secrets instead? I'm Jon McColgan, and you're watching Astrum. Join me today as we dispel the murk and the mystery around the new era of quantum satellites and communication, and reveal exactly how quantum encryption could change our world forever. Tricks to keep our messages secret have been around for thousands of years, almost as long as humans have had written secrets. For example, Julius Caesar used a cipher in his messages to appear like unintelligible nonsense to an enemy, but they could be easily decoded by his generals or friends who knew the trick. The idea Caesar used was simple. For every letter of the alphabet, he simply replaced the letter with another letter a set number of places further up or down the alphabet. For example, if he moved everything right 3 spaces, then A would become D, B would become E, and so on. X would wrap around the alphabet to become A. In this way, Caesar could keep vital information secret, garbling phrases like this one. But as long as you knew the number of places he moved the letters along, in this case 3 to the right, then you could easily move everything back to reveal the true and important message, Astrum is great. In this case, that single piece of information, 3 to the right, is the key that allows you to unlock the cipher, and encryption has been making use of this same essential concept ever since, albeit with a little more complexity. Unfortunately, this cipher has an obvious weakness. There are not that many letters in the alphabet, only 26. So if you came across a message encrypted with Caesar's cipher, you could try moving everything along once, then twice, and so on until the words started making sense. At most, you'd only need to try moving letters 25 times, and you could crack Caesar's code. It would only take a few minutes to know if you were on the right track. This method of encryption hacking is known as a brute force attack, making guesses at the key again and again until the encryption lies decoded at your feet. It is a valid strategy, provided there aren't too many options of what the key could be. Of course, encryption experts over the years worked out more and more complicated ways of jumbling up the letters to make it harder and harder to crack through brute force. For instance, why keep all the letters of the alphabet in order? Keyword ciphers don't worry about that. This second type of cipher works by simply deciding on a keyword and then laying the rest of the alphabet in their normal order after that keyword. Using the resulting jumble as the starting point of your cipher means that a code cracker will never be able to break your code by simply moving everything along. Now they need to know the keyword. Or do they? Technically, with sufficient patience, this type of encryption is still crackable even without the key. Of course, there are approximately 403 septillion ways you could rearrange the alphabet, which naturally would take far too long to try each option individually. If you tried one arrangement, it would take longer than the history of the universe. But it is still technically crackable through brute force if you find a way of speeding this guessing process up. It would take humans far too long to do something like this. But once the computer was invented in the early 19th century, encryptions that were not robust enough could fall to computers making guesses much, much faster. If a human guessing is like a hammer hitting the door, computers are like jackhammers. Modern CPUs can perform billions to trillions of calculations per second. While it would still take a computer a long time to crack a keyword cipher, trillions are far less than septillions after all, this time can be consistently reduced by bringing more computing power to bear. There is a fear that government agencies like the CIA have secret supercomputers with endless CPU, brute forcing their way through the encryption of messages. To combat this, modern encryption does not specifically rely on ciphers anymore. Instead, many types of encryption, such as the widely used RSA crypto systems, rely on complex mathematical problems for which there is no known algorithm a computer can use to solve them. RSA works by taking two massive prime numbers and multiplying them together. The resulting number, called the modulus, is part of the public key that is shared with others. To unlock the encryption, a hacker needs to know which two prime numbers were used to create the modulus. And there's no easy way to factor it back into its prime numbers. Even a supercomputer would struggle. Ultimately, the principle behind encryption has increased in complexity, but mostly works under the same basic idea. Messages are muddled by mixing them up according to some kind of rule, and if you possess a certain key, the message can be unscrambled. Technically, those messages can be unscrambled through brute force methods even without the key, but the keys have become so complex that even with powerful supercomputers, brute force methods supposedly would take thousands of years to be effective. So, our messages are safe then? No, because there is a point of vulnerability. If you want to decode an encrypted message, the sender of the message still needs to give you the key. If this key can be intercepted, the encryption can be undone without any need for brute force methods. And so we turn to quantum encryption, and what China just achieved with the Mozi satellite. For 4 decades, scientists have theorized about a method of sending encryption keys that is completely, irrefutably unhackable. Very cleverly, they don't rely on simply being too complicated for hackers to bother, but rather utilize the fundamental principles of the universe, the principles of quantum superposition and uncertainty. We know that particles, although they appear solid and immutable up here in the regular world, behave very strangely on a small enough level. Specifically, they behave like particles and waves at the same time. Now, you can measure the position of a particle, but you'd struggle to determine its momentum. On the other hand, a wave's momentum is easy enough to measure, but you'd have to settle for measuring its wavelength rather than its exact position. The result of this is that we cannot actually know both the speed and position of particles at a quantum level at the same time, at least not with a good deal of uncertainty. This is known as Heisenberg's uncertainty principle, and is a proven fact of quantum physics. Weirdly enough, we also know that once the particles are observed, they settle on one of the two states. It has been proved through experiments like the double slit experiment that a single particle can travel through multiple paths at the same time, and only settles on one path or the other once it is interacted with. Until then, it travels down both paths in what is known as superposition. left and right. Like Schrödinger's famous cat, neither alive nor dead until the box is opened and it is seen. These principles of quantum physics make it so that once a particle is observed, it behaves differently from when it is not observed. And in the early 1980s, scientists realized that you could incorporate this into a very safe way to send encryption keys. If you converted your encryption key into something physical, a stream of photons for example, and came up with a clever enough method, it would be possible, through statistics, to see whether your photons had been observed or not between the sender and the receiver of the key. In other words, it would be possible to see whether some sneaky hacker had intercepted your encryption key in transit, noted it down, and then sent it back on its way to its original recipient, hoping to remain undetected. According to the principles of quantum superposition, the moment such an observation occurred, the key would subtly alter, and this alteration could be detectable with the right know-how. And knowledge is power. If you know whether your encryption key is observed or not, you can hold off on sending the private message until you have confirmed you have an unobserved key. The message itself can then be safely transmitted through the regular channels. This is brilliant. Of course, getting particles to travel long distances in a state of superposition is not actually very easy. If they bump into an atom along the way, it could collapse the superposition. But scientists realized that this problem could be minimized if most of the journey was done in a perfect vacuum, or, in other words, if the particles could be transmitted through space. And it is China that first brought this theory into reality. Just 1 month ago at the time of writing, on the 19th of March 2025, Chinese scientists announced that they had broken a record for using a satellite to distribute a quantum key between Beijing and a South African university near Cape Town. To do it, they used a tiny microsatellite called MOSI, which sent pairs of entangled particles across the massive 12,900 kilometer distance. Each individual entangled pair had a risk of collapsing en route, but with enough pairs, recipients on each end could compare parts of their code and statistically verify that their particles, and thus the key they were carrying, were either observed or unobserved. MOSI is only 23 kilograms, an order of magnitude smaller than previous attempts at a quantum satellite, and the successful completion of its mission opens the way for an entire distributed network of interconnected quantum satellites, transferring quantum keys across the globe so that people can send messages in safety. Imagine a world where every financial transaction, every email, and the entire internet was completely unhackable, where true privacy was a guaranteed fact of life, thanks to watertight encryption. For those who value such privacy, it will be a utopia. Or will it be? Is it all a little too good to be true? There is one facet of this that gives me pause that nobody seems to be addressing. Quantum key distribution works via satellites distributing quantum keys, which are completely unhackable, all well and good. But note what I'm saying there. They distribute the keys, not the messages themselves. In my research on this subject, I have repeatedly seen the assertion that the encrypted messages can be safely sent via the normal channels because you are able to confirm via quantum key distribution that no one has intercepted your key. The reason they do this is because quantum technology is not yet very good at sending large amounts of data. A key is fine, but a larger file is better sent through conventional means. This is very clever and seems logically very sound, but how is this any safer from brute force methods than current encryption? Brute force methods work by guessing keys, one after another. they do not work by intercepting keys. Certainly there are hacking methods that do work by trying to intercept the key, as this is far easier than the vast computational power required by brute force. But if you do have access to a powerful enough computer, I've not found an explanation for why you care if the key is quantum or not. Either way, it's the encryption itself that is the defense, not how well you've hidden the key. I also imagine a world where hackers don't care if they're noticed or not. While this would mean that the secret message was never sent because a safe key was never found, if hackers just kept their eye on a satellite, it would effectively deny the use of that satellite to its owner. Denial of service attacks are a nefarious method hackers use to bully people into giving them what they want. Imagine if your vastly expensive quantum satellite could be rendered a useless hunk of metal because too many messages were getting intercepted. All in all, quantum encryption is still working out some of the kinks. But if you want to browse the internet behind a safe layer of encryption right now, the sponsor of today's video, NordVPN, is fantastic. Their encryption is robust, making it much harder for hackers or advertisers to track what you're doing online. They can also constantly monitor the dark web for you, so if some of your data does get out, you get warned and can change your passwords. But first and foremost, NordVPN is a VPN, the fastest in the world, which means you can access content from any country, no matter if they're region specific. So if you don't want to wait for a quantum satellite to protect your data, and as I was saying, those are a little fishy anyway, scan my QR code or click on my link in the description below. Using my code Astrum at checkout will give you 4 extra months on NordVPN subscription and directly support the channel. But back to my first concern with quantum satellites. Certainly you might point out that most people do not have access to powerful supercomputers. So for the average hacker, brute force methods are simply not an option. But a new technology is coming that could change all that, and it is also using that magic word, quantum. Experts believe that the first publicly available quantum computer is just a decade or so away. Quantum computers likely won't replace all classical computers. They're a bit niche, and some general everyday tasks like browsing the web are actually just as fast on a classical computer as a quantum one. But thanks to a quantum computer's ability to compute using qubits that can be in a variety of superpositions at once rather than just bits that can either be 1 or 0, there are certain specific tasks quantum computers are much faster at, scarily fast, unnervingly fast. And one of the tasks it's thought they'll be much better at is brute forcing encryption. This is not a hypothetical technology. Quantum computers are already here, in the hands of powerful corporations and governments. In 2015, Google claimed that its D-Wave computer had proven itself 100 million times faster at performing certain tasks than a regular desktop computer. For reference, it supposedly did in a second what a regular computer would take 10,000 years to do. Think of the implications of that. Modern encryption is only safe from brute force methods because encryption is so complex nowadays that it would take a computer thousands of years to work through all the possibilities for keys. But what happens when quantum supercomputers get into the hands of every hacker out there? When those encryption methods, praised for being safe because they would take thousands of years to hack, are crackable in moments. Suddenly, no regular encryption is safe anymore. This is not just me being alarmist. The US government fears this too. The International Institute of Standards and Technology, an agency within the US Department of Commerce, is so concerned about the arrival of this technology that they are telling companies to start preparing for it now by changing the fundamental nature of their encryptions. After all, although quantum computers are not here yet, there's nothing to stop hackers from collecting encrypted messages and financial data now, and then just holding on to them until the day arrives that they can get their new quantum computer from the shops. Passwords, financial transactions, and certain sensitive messages will still be sometimes relevant a decade from now. And once those messages are all cracked with ease, a wave of crimes and exposed secrets will sweep across the world. But there is hope. The NIST has been compiling a defense against the threat posed by quantum computing. And this defense does not lie in unhackable quantum keys, but something more mundane: algorithms. Yes, similar in idea to the algorithms that are protecting encryption already. However, rather than protecting messages by scrambling them with complex mathematical problems that will take a long time to solve, the NIST is preparing 5 algorithms that don't care how much computational power you have. For instance, their FIPS 204 standard makes use of mathematical lattices, points in space, with an arbitrary number of dimensions to work in. The key requires you to find a particular pattern within the lattice, like locating the specific path in a 5D maze. As there is no known mathematical algorithm that can find this path efficiently, there's no algorithm that you can give to a quantum computer. They struggle with the extra dimensions and can't solve the problem any faster than a classical computer. To put it simply, it doesn't matter how strong your muscles are if you don't know where to hammer. FIPS 204 is an example of a quantum-resistant or post-quantum algorithm. Companies like NordVPN are already starting to implement these forms of post-quantum encryption. While it's not completely rolled out, they're preparing already for what's to come. And we're back to where we started. A new technology has emerged, and both hackers and encryption experts are handed the same new toys. Each made massive advances in their field, but as with the rise of computers, the situation stabilizes. Computers threatened privacy, but then ultimately restored it. Quantum technology both improves privacy and finds new ways to threaten it. The cycle of history repeats itself, with developers creating new algorithms and hackers trying to find points of weakness. And each success on one side drives the other to try all the harder. So, have quantum satellites ushered in an era where privacy is guaranteed? I highly doubt it. Even if the key is completely secure, hackers can always find another way in. But equally, has quantum computing ripped down every defense and ended secrecy forever? I also find myself skeptical. Brute force might soon be more effective as a hacking tool, but already companies and governments are pivoting to new defenses that can weather the coming storm. But who can say for sure? Right now, the future is in a sort of superposition of its own, both secure and unsecured, private and public. And much like all things quantum, that superposition will only collapse once it is observed firsthand. Thanks for watching. This video was in part made possible by all the Astrum nauts on Patreon. If you think these videos add some educational value to the world and want to give them more stability than the algorithm, you can become a paid member on Patreon to contribute towards their creation. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Just sign up with the link in the description. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.